Problem 1, inverse trigonometric functions. So starting with the y equals cosine of x function, we can see that the domain is at 0, pi, and the range is at -1, 1. But with the inverse cosine, it's the flipped version of the domain and range. So now the domain is going to be -1, 1, and the range is going to be 0, pi. So they just flipped, basically. And so we can see that with the inverse, we have the output is the angle whose x value on the unit circle equals the input. So what do I mean by this? Here's some examples. So basically, in order to do both of these, we have to be mindful that we have to be between 0 and pi. The output has to be, which is the angle. So it's restricted to the range. So with the inverse cosine square root 3 over 2, it's basically asking where on the unit circle is the x value going to be square root 3 over 2, and that's at angle pi over 6, and we can see the point here. So basically, it's just saying that this input, it belongs to this output, which is this angle, within this restriction. Same thing over here. Where on the unit circle is the x value going to be 0 within that restriction? It's going to be pi over 2. This is the x value within that restriction of this output being pi over 2. Here's the point. We can see these 2 points being graphed right here. Okay? And then we move on to y equals sine of x. Here's a typical y equals sine of x. The domain is -pi over 2, pi over 2, and the range is -1, 1. But within our inverse, it's just flipped. -1, 1 is the domain. -pi over 2, pi over 2 is the range. And so we can see that the output is the angle whose y value on the unit circle equals the input. So basically what I mean by this is looking at the examples, and again, we have to be mindful that we are restricted of the range -pi over 2, pi over 2. And so when we look at this, it's saying where on the unit circle is the y value going to be 1/2. That's at the output pi over 6. So this y value, like that is the input of this output. And here is the point. Over here, where on the unit circle is the y value going to be -1/2? That's at -pi over 6. And so this is the input of this output, this angle. This is the y value of this angle. And here's the point, and we can see it right here, these 2 points. And so I just want to mention that this is where the restriction occurs if we're looking at a unit circle from pi over 2 to -pi over 2. For cosine, like the inverse cosine, the restriction would be from 0 to pi on a unit circle, looking like something like this, kind of like the way I'm drawing it. And also with sine, the restriction basically makes it not allowed to use coterminal angles. So it just have to be -pi over 6 instead of it being 11 pi over 6. We don't use coterminals with sine, with inverse sine, like when we're trying to find inverse sine. Problem 2, solving trigonometric equations. So basically, here's our first example. It's 2 sine of 3x minus 1 equals 0. First, we will isolate the sine of 3x, and so we do that, and we get sine of 3x equals 1/2. And then we do the inverse to cancel out that sine value, and so we're left with 3x equals inverse sine of 1/2. So where on the unit circle would the y value be 1/2? And we don't look at the restriction -pi over 2, pi over 2, because we are looking at finding all solutions of the equation. Okay, so we're not doing restrictions in this case with sine and cosine. And so we get 3x equals pi over 6 and 3x equals 5 pi over 6. So then what we do is we end up writing the plus 2k pi on both of them, but then we have to divide by 3 to get that 3 out of there, out of the x, so x can be isolated. And so all solutions would be x equals pi over 18 plus 2k pi over 3, and then x equals 5 pi over 18 plus 2k pi over 3. Now, with actually looking at the solutions in the interval, we basically just do k equals 0 through 2, since that is going to be less than 2 pi. It would have went higher and greater than 2 pi which, if we went to k equals 3, which we cannot do this in this case, in this problem. So now we have to put the 0 in for k. We would just get pi over 18 and then 5 pi over 18. When we put k as 1, we just get, like this would be the equation now, it would just be a 2 pi over 3 with those angles. And so 2 pi over 3, and then we get 3 pi over 18, and then 17 pi over 18, and lastly with k equals 2, that would allow us to get this 2k pi over 3 to be 4 pi over 3, leading us to being pi over 18 plus 4 pi over 3, and 5 pi over 18 plus 4 pi over 3, and we get 25 pi over 18 and 29 pi over 18. So all of these in the boxes are the solutions in the interval 0, 2 pi. Now, looking at the next problem, we have part B of tan squared x minus tan x minus 2 equals 0. So we would use this to basically do a factoring equation. So instead of looking at the tangent, we just make it x's. And so we do a factor, what multiplies to -2 but adds to -1, -2 and 1. We input those in the equation, factor out that, and we end up getting this x minus 2 and times x plus 1 equals 0, which then we input the tan instead next to the x. And so we then get tangent x equals 2 and tangent equals -1. We do inverses on both of them so that we can get x by itself. We get x equals tan -1 of 2. And so there's no special angle on the unit circle that has this. So this wouldn't even be a solution. This wouldn't even be considered a solution. So it's basically just a no-go. But then over here, the x equals tan, inverse tan of -1 would actually be saying like we're on the unit circle with that restriction of -pi over 2, pi over 2, because this is tangent. We need a restriction on tangent, on inverse tangent, I'm sorry, would be like where on that restriction would the tangent be the inverse tangent, the tangent be -1. And that would be x equals -pi over 4. So all solutions would just be x equals -pi over 4 plus k pi. And so that would be that. Problem 3, trigonometric identities and quadratic type equations. So for A, we have the first equation is 2 cosine squared x minus 7 cosine x plus 3 equals 0. And we're going to treat this like factoring as well. So we replace the cosine with just like removing it. So now we have this 2x squared minus 7x plus 3 equals 0. We factor, 1 multiplies to 6, but adds to -7, -6, and -1. So then we input those, and then we factor, and we get 2x minus 1 times x minus 3 equals 0, which leads to, then we input the cosine in there, so that's 2 cosine x minus 1 times cosine x minus 3 equals 0. Get cosine of x by itself. Let's start with this one first. We get cosine of x equals 1/2. We want to get x by itself, so put the inverse on both sides to cancel out cosine. And so we have to figure out where on the unit circle without restrictions, because we are not considering restrictions in this case for these types of problems, would the x value be 1/2? Well, it would be at pi over 3 and at 5 pi over 3. But then over here, we got cosine of x equals 3. And why would we even do the inverse? It's not even worth it, because no solution for this particular part of the problem, because there is no special angle on the unit circle that's going to have an x value or input of 3. So no solution for that part. That's not a solution. So we would only get x equals pi over 3 plus 2k pi and 5 pi over 3 plus 2k pi. Now for part B, we have the equation 1 plus sine of x equals 2 cosine squared of x. So we were given a hint to use this sine squared x plus cosine squared x equals 1. And we can basically get cosine squared x by itself, which leads to 1 minus sine squared x, to simplify this cosine squared of x. So input that in there, and then we can distribute that 2, which leads us to 2 minus 2 sine squared of x, and of course we have the 1 plus sine of x. We want to then get a kind of like quadratic equation happening. So then this is the a squared plus b squared plus a squared plus bx ax squared plus bx plus c equals 0, basically. And so then we want to factor, and so we get 2 and negative 1, factor, and then we end up getting 2x minus 1 times x plus 1 equals 0. We input the sign with that x, and we end up getting sine of x by itself in this case. And so that will be asking us where on the unit circle without restrictions is the y value going to be 1/2. That's going to be at pi over 6 and 5 pi over 6. Over here, where on the unit circle is the y value going to be negative 1? That's going to be at 3 pi over 2. So we have 3 answers. So x equals pi over 6 plus 2k pi, 5 pi over 6 plus 2k pi, and 3 pi over 2 plus 2k pi. Problem 4, sketching polar graphs. So starting with the question A, within this question, is r equals 2 plus 2 cosine theta. So what I like to do is start with just drawing a cosine graph. This is the typical one, the one that's dashed. And so we can see that we're multiplying by 2 each of these values, wherever it is, like each of these values, and we're also adding 2 to them. So multiply by 2 and add 2 for all of these values from the original cosine graph. So now we end up getting, like, for 0 is 4, pi over 2 is 2, pi is at 0, 3 pi over 2 is at 2, and 2 pi is at 4. So we can see to make our cardioid graph, what happens here is we say, okay, at 0, we're going to the radius of 4. So we go here. And we drew these lines to show the radius. Okay, these dashed lines to show the radius. Then at pi over 2, we go to 2. So pi over 2 goes to 2. And then those are like basically, those are the radius, the radii. And then for pi, we're at 0, so we just go at 0. For 3 pi over 2, we're at 2, so we go right here. And then for 2 pi, we're at 4, which is also going to be here. That's why I put for, like, this is polar form for these points. So that's why I have the 4, 0 and 4, 2 pi, and that's why the order looks like that. And so we can see 2, pi over 2, 0, pi, 2, 3 pi over 2, and then here's the same, 4, 0 and 4, 2 pi. So since 4, 2 pi is actually the same point as 4, 0. And so for this equation, the intercepts show the max, min, and origin crossings, revealing the cardioids' size and orientation. These, like, radii and all of this from this graph right here demonstrates that this shape, which is a cardioid, is happening in this equation. This equation is a cardioid graph. So for B, which is r equals 1 plus 2 cosine theta, what's happening here is that I like to draw again my typical cosine graph in the dashed. And so what's happening is we're multiplying by 2 and we're adding by 1 to each of these points on the dashed cosine original graph. And so we end up getting, like, at 0, we have a 3 radius, pi over 2 has 1 radius, pi has a negative 1 radius, 3 pi over 2 has a 1 radius, and 2 pi has a 3 radius. At 2 pi, there's a 3 radius. And so these points tell you where the radii are for each. And so the circles are your zeros, and you need these in order for a lemicon graph to actually be a lemicon graph. So we set this problem equal to 0, and so we end up solving. And so where on the unit circle is the x value going to be negative 1/2? Without any restrictions in these situations, in these problems, we have that theta is going to be 2 pi over 3 and 4 pi over 3. These are the zeros. So we draw the lines, 2 pi over 3, 4 pi over 3, and so we start. So we're like, okay, at 0, the radius is going to be 3. So right here. Then we have pi over 2, the radius is going to be 1, so right there. For the 0, we basically, it's just at 0 because they're both, the radius is just 0. So 0 for both of them, And then for pi, it's at negative 1. So pi would be a radius of negative 1, but in this case, it would be this way because the lemicon has a loop. And then, so that would be right there, the negative 1 pi, because again, a lemicon needs a loop. This loop right here. And then We have 3 pi over 2, which is at 1, the radius 1, so right at this point. And then 2 pi at 3, the radius is 3 for 2 pi, which is right here. And so you can see that for both these, it's plotted right there. And also you can notice that it's also going to have a 3, 0 right here. They're at the same, this is the polar form. They're in the same point because the radius is at 3 for 0 and the radius for 2 pi is at 3. So they're the same point, okay? And they're written 2 different ways. And so the intercepts show where the curve crosses the axis and pole, helping reveal the lemmicon's overall shape. So we can see, like, with these intercepts right here, the 2 pi over 3 and the 4 pi over 3, they really influence the shape and how we know a lemmicon is a lemmicon. And also these radii. The radii of each of these pi over 2, pi, 3 pi over 2, 2 pi, and 0 show you that a lemmicon has this loop, this little loop right here. So yeah. And for C, which is r equals 2 sine theta, we can just know from here that this is the radius. But it's sine, so it's the y-axis, so we're at 2, and it's at pi over 2. So for polar version, it's at 2 comma pi over 2, and we also have in polar version 0 comma 0, which is the origin. And also it can be written as 0 comma pi, because pi is right over here, basically. So yeah. And so for this equation, the intercepts at the pole and the maximum radius shows the circle's size, position, and orientation. With this specific radius at pi over 2, really it tells you how this is going to look, what this shape, what this polar graph is going to look like, and also because it's sine. And these points also influence it as well on how it will look. Problem 5, complex numbers in trigonometric form. So here I have z equals 1 plus I, and I graphed it at 1 comma 1, which is right at this point. I also sketched out these, and basically what you're supposed to do is you're just supposed to distribute whatever you have, like the 2, the negative, the 1/2, in this equation. Okay, so distribute those, like the 2, the negative, the 1/2, using this equation, distribute them, and so you get these. And so I graphed them as well on here. As you can see, we have -1, -1, 1/2, 1/2, 1/2, 1/2. We have 2, 2, 2, 2. So yeah, and then 1, 1, of course. And then over here, we have to find the modulus and argument. So I use to find the modulus, square root a squared plus b squared. And we just take a and b, which is 1 and 1. We get square root 2. And then for the tangent theta, we ended up having to do b divided by a, which is just 1. And we get pi over 4 because we're at the quadrant 1, which is pi over 4, and that's where tangent equals 1 with positive x and y's, or a's and b's. Same thing over here. We end up getting 2 square root 2. I just simplified this, square root 8. And I did that by doing 2 times 4, but they were each square rooted. And so square root of 2 is, square root of 2 just stays square root of 2, so it's right here, and then the square root of 4 is just 2, so it goes on the outside, and then you have square root 2. So you get 2 square root 2, and then theta would be pi over 4 as well, because it's in quadrant 1, because 2 comma 2 is positive, and tangent would be 1. So that's why pi over 4 is that theta for this equation. And then for this equation, the negative z equals -1 minus 1, we end up getting square root 2 as our modulus, and then 1 for the tangent. But because a and b are both negative, that's going to fall in quadrant 3, which is where 5 pi over 4 is going to be, and the tangent will be 1 there. And then we can see here, we get square root 2 over 2 as the modulus, and then our tangent ends up becoming 1, and because they're both positive and because the tangent equals 1, the theta will be pi over 4. And then what happens is we then end up putting it in trigonometric form. We wrote it in trigonometric form, which you can see here, which is the radius, and then the cosine theta, and then plus I sine theta. we do it with all of these right here shown, just basically using what I solved for from previous step. And then here, these are describing explaining the transformations. For this equation, we scaled by 2, twice as far from the origin, same direction. And so then with this, negative z equals negative 1 minus I, it's multiplied by negative 1, and it's reflected through the origin, same distance. And then for 1/2 z equals 1/2 plus 1/2 I, it's scaled by 1/2 and half as far from the origin, same direction. For part B, we have z equals negative 1 plus I square root 3, basically doing the same thing, again, distributing these like 2, negative 1, 1/2 to this equation. And so we get those, and we put them on the graph. Again, just plot them. Square root 3 over 2 is less than square root 3 and 2 square root 3. And so we plot them all, and then we find the modulus like we've been doing and the argument. And then what we have to do is, once we find those, and again, it all depends on as well, not just what the tangent is, but also what are your signs for A and B. So if they're negative x, negative a, and positive b, that would be in quadrant 2, so that's why we got that theta. Here, same thing. Here, it would be different because we are we're trying to find at 1 comma, the a is positive now, so 1 comma, so 1 a is 1, and then a negative b, so that would be 5 pi over 3, which is in quadrant 4. And then here it would be 2 pi over 3. But we're basically doing the same thing as part A. And we found we wrote in trigonometric form all of them, just using what we solved for in the previous step. And then we are going to explain the transformation. So for this equation, we scaled by 2, twice as far from the origin, same distance. Negative z equals 1 minus I square root 3 multiplied by negative 1 reflected through the origin, same distance. 1/2 z equals negative 1/2 plus 1/2 I square root 3 scaled by 1/2, half as far from the origin, same direction. Problem 6, systems of linear equations and Gaussian elimination. So basically here we have this problem, and I labeled each row 1, 2, 3. We're going to use 1 and 2 so that we can eliminate this x on the row 2 equation. So we multiply by a negative 1 for row 1, and we cancel out the x and do all the math. We get 4y minus 4z equals 12. Then here's what our full problem looks like now. We need to take 1 and 3 so that we can take out this 3x on row 3's equation. So negative 3 is going to be multiplied to 1, and then we end up canceling out that x, and we get 8y minus 14z equals 0, and this is now what it looks like. Now, lastly, we need to eliminate this y, so we're going to take 2 and 3. We're going to multiply by negative 2 so we can cancel out the y, and we get negative 6z equals negative 24. Divide by negative 6, and you get z equals 4, and this is what the problem looks like now. Well, now we need to use back substitution by taking that z and inputting it into this formula to get y. And so we do 4y minus 4 times 4 equals 12. Do the math, we get y equals 7. We know z equals 4. And lastly, to find x, all we have to do is input it in the first equation. So we input y and z, so x minus 2 times 7 plus 3 times 4 equals 1. And we get x equals 3. And so we get x equals 3, y equals 7, z equals 4. In this problem, each variable is solved exactly. We have a unique solution, we have solutions. But the next problem that I'm about to discuss is going to be a bit different, actually a lot different. And we get a different result and different answer at the end. So here's our problem. I, again, did the same thing, labeled them. I take 1 and 2. So that I can eliminate this x in row 2, because we're trying to make it look like a triangular system. We are trying to get it from this to a triangular system. So multiply by negative 2, cancel out those x's, you get negative 2y plus 3z equals 4. This is what our problem looks like now. Now we need to take 1 and 3 and eliminate that x right here. So we take a negative 3 so that we can eliminate the x's. And I get negative 2y plus 3z equals 2. And this is what it looks like now. Lastly, to make it look like a pretty triangle form, where we just take this part out and this will be like a triangle. Now I need to take row 2 and 3 and eliminate that y for row 3. And so you have to eliminate the y in row 3. So I take negative 1, cancel out the y's, and we get this problem. We eliminate 2 y's, the 2 and the negative 2y, and the negative 3z and the positive 3z. And we're left with 0 on this side equals negative 2. That's not a true statement. 0 does not equal negative 2. This shows that this particular system is no solution. We don't have solutions. This is no solution.